it was entirely due to his presence. Together with the presence of people like Buxbaum and great topologist Jerome Levine, it was pure gold, Aparanji as we call in Sanskrit. I will forever be grateful to him for not only uh, imbibing imbibing in us the dynamic joy of doing mathematics, but also attitude towards academic life, however tardy I have been in imbibing. Thank you, Professor Eisenbud. It's such a joy to introduce you. As you know, Professor Eisenbud is a professor at University of California, Berkeley, and director of MSRI. And he will be talking today on layered resolutions and Cohen-Macaulay approximation.
Thanks, Puna. It was fun to have you and Francisco as students. You spent most of the day, as I recall, in the Commons room arguing with each other about matters large and small. And I believe you still do that.
Yes,
you have a passionate personality, which really made Brandeis lively in that period. It was very nice. So I want to talk about some material which I was already interested in before that time. I guess a good 40 years ago, I wrote a paper about modules over hypersurfaces and complete intersections. It was rather ambitiously called Homological Algebra on Complete Intersections. And the hypersurface case has turned out to be quite the right thing. The complete intersection case, not quite so much. And in recent times, Irena Peyeva and I have worked on this again. And we have what I think is in some way the right approach to the complete intersection case. And that's what I want to tell you about today. This appeared recently in the Journal of the European Math Society in 2021. So you can read the details for yourself. I'm not going to prove very much because the constructions are in some way the main thing. The proofs are not so hard. And the constructions take a little while to describe. But first, let me go back to 1980 and tell you what I knew then and what I think most of you know now. You heard a nice talk by Graham Lushke a few weeks ago. I looked at the recording of it, and he talked about something built on this notion of matrix factorizations. So the idea is to go from a regular local ring, let's say, where by Hilbert's syzygy theorem, all resolutions are finite, to the next cases. And the next case seems to be codimension 1, namely the case of a hypersurface. And so if you take R to be S mod 1 equation F, then resolutions of modules over R, every R module, finitely generated, I guess. I will always assume things are Noetherian and finitely generated and all the finiteness assumptions that you like. And in this case, every R module has a free resolution, minimal free resolution, which is eventually periodic. R free resolution, I should say. Of course, it has an S free resolution too. It's also an S module, and that will be finite. But the R free resolution can be built from the S free resolution in a simple way and becomes periodic. This is a vague statement in a sense, since it only says eventually periodic. but you can be more precise and say what happens. So as you resolve a module, the depths of the successive syzygies go up until they reach the depth of R. And at that point, you have a maximal Cohen-Macaulay module. So some syzygy, the dimension of rth syzygy, for example, is a maximal Cohen-Macaulay module. So we might as well start with that and suppose that M is a maximal Cohen-Macaulay module, which I'll always abbreviate MCM, maximal Cohen-Macaulay. Macaulay doesn't quite fit. And in that case, M has almost a periodic resolution, but M might still have a free summand. So I'm going to assume that it has none, no free summand. After all, the module you started with might have had finite projective dimension, in which case M would be free if you take that syzygy. But it might well have a free summand. However, if you go one step further, then there will be no free summand for sure. That's an easy result about Gorenstein rings. And in that case, then M has a periodic resolution of period 1 or 2. And they're easy to describe, these periodic resolutions, because the projective dimension of M as S module, all right, PD SM, is exactly 1. That's the Auslander-Buchsbaum formula that says the projective dimension plus the depth is equal to the dimension of S. And since the depth is the depth of R, which is the dimension of S minus 1, then this formula gives the projective dimension of M as 1. So M has a resolution, M, S to some power. And of course, M is a torsion S module, so the syzygy has the same rank as N, but in fact the syzygy is free because it has projective dimension 1. So the resolution looks like this. Let's call this map A. And M is annihilated by the equation of the hypersurface. I called it F before. So Fm equals 0 implies that you can lift multiplication by F along A. So in other words, there's a homotopy. Let's call it B. There exists B, such that if you first go by B and then by A, then you get F times the identity. And this is called a matrix factorization of F. You heard about all this from Graham. The first time this appeared, as far as he or I know, was in work of Dirac, who needed to take the square root of an operator. And of course, he had a polynomial F representing the operator, which had no square root. So he needed to do something. And he was able to get the square root by taking first a matrix factorization and then expanding it to get a factorization which gives the square of a matrix. If you take 0, A, B, 0, and square it, you get F times the identity. So he had a square root of whatever he wanted. So in this way, you can factorize, in fact, any power series as long as it has no constant term, or you can take square roots of any power series. It gives you a very great flexibility. But this is what a matrix factorization is. So this works, of course, if F were non-singular, so that R would be a regular ring again, then the only matrix factorization could be zero factorization, because you wouldn't be able to take the syzygy. The syzygy M would be zero itself, so there wouldn't be any matrix factorizations. But matrix factorizations and their presence somehow measure the singularity. And people have run with this, first Buchweitz, and then a lot of physicists discovered this. And there are singularity categories made of matrix factorizations and derived singularity categories, etc. I'm not going to go down that path. I want to tell you something much more concrete than that. But there is a whole literature about singularity categories and what you can do with them, which is, I think, quite interesting also. So that's the situation as of 1980. But I did do one other thing. I said, well, what about in the case when R is S modulo F1 up to, let's call it F sub C, a complete intersection. Codimension C. Then there's an analog of this theory, which is good as far as it goes. So you have a you again take an M maximal Cohen-Macaulay over R. You take an S-free resolution, M S to the beta 0 up to S to the beta something, whatever the dimension is. And then there's a family of homotopies and higher homotopies. So if you have a homotopy for multiplication by even F1 on this, then its square turns out to be homotopic to 0. And in general, the homotopies are homotopy commutative, and then there are higher homotopy commutativities. I've learned in recent times from Jesse Burke that this is really part of the theory of A-infinity algebras. Oops. But anyway, I understood it in 1980 as higher homotopies. And you can use them to construct a resolution. Which is really, if I call this original resolution F, then you can take F, tensor it with R. Now it's not exact anymore. And then tensor it with the divided power algebra on C variables. So I'll write that as R of x1 up to xc, new variables, dual. That's the divided power algebra. As a module, it's just isomorphic to the polynomial ring. So you can make this into a complex, which has this as an underlying free module. So this is graded. The x's have degree 2. These are the homological degrees. And so you get a resolution. From the point of view of A-infinity algebras, this is really using the A-infinity module structure on M over the A-infinity algebra, the rather trivial A-infinity algebra, which is the Koszul complex of the F's. So that's a general construction. And the problem is that it's almost never minimal. Rarely a minimal resolution. And if you've thought about free resolutions much, then you know that minimal resolutions are really much more useful than non-minimal resolutions. You can read off lots more invariance from them. So I wanted to have then a minimal resolution. I didn't know how to get it. I made various wrong conjectures about how it might be related to this resolution. This resolution has some kind of module structure or algebra structure. So I thought maybe I could take a quotient of this as an algebra and get a minimal resolution. That's not true. And Avramov produced counterexamples to that later on. So where is the minimal resolution going to come from? And what I want to show you is a solution to that problem. So layered resolutions. Or I'll say often, and I'll explain that later on, minimal. So I want to tell you how to construct the layered resolution of such a module M, maximal Cohen-Macaulay module with no free sum ends. And there are really two resolutions. So in the case of that we've just looked at, there was a resolution, let's say the matrix factorization case, the nice case. There was a resolution over S with some special property. And in addition, there was a resolution over R, which I actually didn't write down. The resolution over R looks like R to the N, A. Well, A times B is F, so that's 0 over R. So I'll put a bar here over A to say I've tensored with R, R to the N. Well, and the R doesn't need a bar, doesn't matter. R to the N, B, so that's a complex at least because AB is F times the identity. And that implies that BA is also F times the identity because of the uniqueness of inverses. Essentially, over the quotient field with the quotient ring of R, B is F times the inverse of A. So the multiplication in the other direction also works, and you can prove that more generally, as long as F is a non-zero divisor. So I can put here an A, still a complex, and in fact, this is a resolution of M. This is the minimal resolution of M. So from a matrix factorization, you both see a nice structured resolution of M over S and a nice resolution of M over R. And there's a little more structure to this. These isomorphisms, I wrote it Rn, 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 but in fact, there's a kind of canonical up to homotopy isomorphism of degree 2 in this resolution, some kind of operator. So there's a good structure on both resolutions, and you get both from the matrix factorization. So that's the picture that I want to imitate with a layered resolution. So there are going to be two layered resolutions. And of course, it's a nuisance to have so much notation, but I will call this one M F1 up to FC. This is going to be an S-free resolution with some extra structure, and the lower layered resolution, so that was the upper layered resolution, the lower layered resolution, M F1 up to FC, will be an R-free resolution. And as I say, both of them will be often minimal, and here always M is going to be a maximal Cohen-Macaulay R module, and F1 up to FC, R is S modulo F1 up to FC, and M should have no free sum ends. And if M has a free sum end, then take a first syzygy, and the first syzygy won't have a free sum end. So this is not really a restriction. And again, this gives you an asymptotic description of every resolution. So these are the objects I want to describe. This is really the goal of this talk. Now, I need one tool which is very beautiful and very elementary, but not as well known as I think it should be. This is something which got studied for a while around 1990, and then hasn't appeared much since then, but I think it's a very lovely idea. And this is the idea of Auslander and Buchweitz. Oops. I got an extra line there. Auslander and Buchweitz. This was published in 1989, I think. Let's see. Yeah, 1989. And it has the following form. Suppose R now is a Gorenstein ring. Actually, they did it in a slightly more general case of a arbitrary Cohen-Macaulay ring, but the result is less, I don't know, less elementary looking. And so at the time, I kind of ignored it, I have to say. This is a case where less generality is better, at least from my point of view, because it gives you more of a feeling of what's really going on. But anyway, take R to be a Gorenstein ring, local, and M any module. Then there's a maximal Cohen-Macaulay module, which is the best approximation to M. And of course, M might have a free sum end, so we have to allow free sum ends in our maximal Cohen-Macaulay modules now. But anyway, we can make a maximal Cohen-Macaulay module, and in fact, an exact sequence with a universal property and a very nice form. So there exists a what I'll call the approximation sequence. And the form of that is you start with M, and then there's going to be a surjection, of course, from a maximal Cohen-Macaulay module, but I'm going to take it to have a particular form, M prime plus, I'll write B naught. So B naught is going to be the free part, and M prime is maximal Cohen-Macaulay over R, and has no free sum end. Over a local ring, you can always do this in a unique way. You can split a free sum end off a module in this way. And the kernel, I'll call B1, also has a special property. B1 has finite projective dimension. Finite projective dimension. So you build any module out of a maximal Cohen-Macaulay module and a module of finite projective dimension. The general Cohen-Macaulay case, B1 wouldn't have finite projective dimension, but it would have a finite resolution by sums of copies of the canonical module. And since the canonical module is a fairly mysterious object, that seems less concrete. But this is very concrete. And there's one additional remark about it, really. So if the module M is itself Cohen-Macaulay, not maximal Cohen-Macaulay, of course, then it would be equal to M prime. If it is Cohen-Macaulay, let's say of codimension 1, You could do this for larger codimension too, but I don't need it. Then B1 is free. Oops, sorry. Is a free module. In general, you can tell the projective dimension of B1. It's just one less than the codimension or than the codepth of M, more properly. Because of Alexander-Buchsbaum formula, any module of finite projective dimension, doesn't have to be over a regular ring, satisfies this. Why is the canonical module mysterious? Oh my God. And Bernd Ulrich and I have written a long, difficult paper about canonical modules of residual intersections, and that's given me new respect and fear of them. But it's hard because it's not very explicit somehow. You can make it explicit in lots of ways. There are the whole theory of Dedekind difference, for example, is aimed at that. But in general, canonical modules, which may not even exist, right, are complicated.
Okay, yes.
They're always defined. Canonical modules don't really have a good definition. They're always defined in terms of other modules or in terms of cohomology. It's hard to say where it is. Anyway, let me not get onto that subject. So, yeah, no problem. So B1 is a free module in this case. And that's the case we're going to use. So a talk should contain a proof of something. And since this isn't so well known and it's easy to do, let me explain why this is all true. So how do you build this exact sequence? Really, the important one is M prime. If I take M prime, that'll be a maximal Cohen-Macaulay module and a map to M. I can always put in a free module to make it a surjection. I just take the minimal number of generators I need to make a surjection. And then B1, well, whether B1 is finite projective dimension or not won't depend very much on B0 because I'm just adding free stuff there. So I need somehow to understand why the B1 should have finite projective dimension as part of the construction. So how do you construct M prime? Here it is. So to construct the approximation sequence, you start with M, of course, and you make a free resolution. What can you do? So F0, it goes on for a while. Let's say you have Fk here, and the kth syzygy I'll call M sub k, Fk minus 1. So the depths of the modules M are going up. So the Mk has depth perhaps as much as the ring, but if not yet as much as the ring, then it has depth, the depth of M plus k. M is really M0 in this. So Mk eventually, Mk is maximal Cohen-Macaulay. And as I've said a few times, the first syzygy over a Gorenstein ring of a maximal Cohen-Macaulay module can have no free summands, so the minimal first syzygy. So eventually Mk is maximal Cohen-Macaulay with no free summand. Now at that point we can reverse course and turn around. So if I look at the dual of Mk and resolve it backwards, I'm going to call this Gk minus 1 star for reasons you'll see in a moment, and go back on. After a while I'm going to let the indices go down, G0 star. I can make a resolution like that. It might go on, of course, but I'll stop there. And then I can take the dual of this resolution and splice it onto the Fs. So I can make F GK, this is MK in between. And of course, the map from GK minus 1 star to MK star dualizes to a map from MK to GK. MK is reflexive in this case, a general fact. And then I can go down to G0. And this, of course, goes on forever, typically. Now, I should have made myself a little more room here. When I made this resolution of the G's, of course, I also have a complex covering MK star, namely FK star, K minus 1 star, etc., down to F0 star. And since these are equal, there's a comparison map. Always goes from the acyclic complex, which the G's are, because I chose a resolution, to, from a projective complex, which the F's are, to an acyclic complex, which the G's are. So I have the map going up in this case, from F to G, and then when I dualize, I get a map going down from G to F. This should have been K minus 1. Fk minus 1 down to F0. And of course, that will induce a map from the whatever the co-kernel of G1 to G0 is, let's call it M prime, to M. So I get a map from M prime to M. Now, when I do this, I didn't explain why the G dual was acyclic, which is, I guess I don't need it even here. But in fact, this upper complex, this thing with F's and then G's, is a resolution. And that's because MK star is, again, maximal Cohen-Macaulay. So the dual of a resolution of MK star is going to be exact. And I could, in fact, go on forever, and it would always be exact. These resolutions, these doubly infinite resolutions exist over Gorenstein rings. So the top is a resolution, but it's all the modules in it are Cohen-Macaulay, maximal Cohen-Macaulay modules, all the kernels. And M prime, being the dual of a maximal Cohen-Macaulay module, is again maximal Cohen-Macaulay. And so I have now a maximal Cohen-Macaulay module mapping to M. This map might or might not be surjective. So I get M to 0, here's M prime, and some map phi. Might not be surjective, but I can make it surjective in a minimal way by adding a free module. So now I have a surjective map, minimal. And the kernel, whatever it is going to be B1. Now, why does B1 have finite projective dimension? If you think about the resolution of M prime or M prime plus B naught, it really doesn't matter, then eventually it coincides with the resolution of M. So if I make a map of resolutions, I take the resolution of M prime plus B naught and a comparison map to the resolution of M, then I can make a resolution of B1 as a mapping cone of that comparison map. And eventually the mapping cone is going to be the mapping cone of the identity map, which is a trivial complex. So that's why B1 has finite projective dimension. So resolution of B1 made from the mapping cone of a map from the resolution of M prime plus B naught to the resolution of M is eventually trivial. Not zero, of course, but homologically trivial. Because it's the mapping cone of the identity map. So that's the proof given by Auslander and Buchweitz. Hard to improve on it. And it's very constructive. You can type approximation into Macaulay 2 and it will spit out these modules and all these maps. There are interesting invariants associated to this. The rank of B naught is got to be called the Auslander invariant. The rank of B naught, which is the number of generators of M not hit by M prime, equals the Auslander invariant. I suppose there are many Auslander invariants, but this is one. And this was studied by Marcinkowski and Ding and a few other people back in the early 90s, but hasn't gotten much play since then. An interesting invariant from my point of view is the kernel of phi. So the number of generators, this is usually called alpha of M, number of generators of kernel B, kernel of phi, let me name it beta of M. That turns out to control the minimality of the layered resolution. So that's an interesting invariant, which is not so easy to study, at least for me, but interesting to me. How am I doing in time? I have some time left, good. So I want now you to use these tools to construct the two layered resolutions. I'll start a brand new page for that, but I'll keep this this approximation sequence on, and recall that in the codimension 1 case, B1 is not only finite projective dimension, this B1, but free. That will be a useful fact for us. So let's construct the layered resolution over S of M. And again, my notation is the same as before. F1 up to Fc is a regular sequence. M is a maximal Cohen-Macaulay module over R, which is S mod F1 up to Fc. You could take S to be any Gorenstein ring, but you'll get finite resolutions if you take it to be a regular ring, of course. So that's the case I want to look at. So this is going to be an S-free resolution of M. So now, as I said, the goal was not only to compute S-free resolutions and R-free resolutions, which we could do with the old technology, but minimal ones, at least most of the time. And the theorem, which I'm not going to prove, but you can make it more precise here too, is that if N is any module over R, then there exists a number of little r such that the rth syzygy, or any higher syzygy, I could say r prime syzygy for r prime bigger than or equal to r, M has minimal resolutions. L upper and L lower. So in some sense, this is the main theorem, But as I say, the main point is the construction. This is analogous to the theorem for a hypersurface, which says that if you take any module over a hypersurface, then its resolution is eventually periodic. This is I think, the right replacement for the periodicity structure. And this is explained in a different way, more equationally. So periodicity, of course, and matrix factorizations are done by two things: an equation, AB equals F, and a depth condition. F has depth 1 as a non-zero divisor. Both kind of trivial-looking conditions. But you can describe the general case for getting a minimal resolution and also for constructing it equationally and in terms of depth conditions too. And that was done by Payeva and me in a different place. So there's an equational construction too. And for that, you can see the Springer lecture notes that we wrote. And this is it. In fact, minimal free resolutions over complete intersections. I suppose it has a volume number, 2152. So that's done in detail there. That looks much more complicated than what I'm about to show you. We discovered it first and only later realized that we were speaking in layered resolutions. Okay, so that's the goal. Let me actually construct something rather than just claiming I'm going to construct it. And it's pretty simple to describe. So it's going to be an inductive construction. Of L upper M F1 up to FC. Well, in terms of the thing with codimension 1 less, of course, L upper of M prime. I'll tell you what M prime is in a moment, but you can probably guess. F1 up to FC minus 1. Where M prime is the essential Cohen-Macaulay approximation. So MCM approximation. And by that I mean the M prime that appears in the approximation sequence. Here's the M prime I want to take. So I'll have an approximation sequence. Here's M prime plus B naught goes to M to 0 and B1. And now notice that R is, I could describe as R prime mod FC, where R prime is S modulo F1 up to FC minus 1. So this is codimension 1. R prime is a Gorenstein ring. It's a complete intersection, so it's Gorenstein. So M is Cohen-Macaulay of codimension 1. So B1 is R prime free. And it looks like we already almost have the beginning of a matrix factorization, right? We have a projective dimension 1 presentation of M. Why not make a matrix factorization out of it? And in fact, you can. In fact, you can take, if you wanted to, I'm not going to use this, but you could, M prime to M, and then B1. And then there's a homotopy again, M prime plus B naught to B1, etc. And you'd get a periodic resolution, unfortunately not by free modules, but, well, something close to free modules. After all, if if R prime were regular, then M prime, which is a maximal Cohen-Macaulay R prime module, would be free. So this is the exact analog of the matrix factorization. And I could build a resolution out of it by taking S-free resolutions of M prime and B naught and just building up a sort of doubly infinite, well, an infinite double complex out of this, and then taking the total complex. That would give me a resolution 2. And actually, it's the same resolution that I'm going to construct for you in a more concrete way. But that's a possibility. But I don't have to do that. So what do I want to do? As I say, I want to use the inductive hypothesis. So this, let's call this resolution in the codimension 1 case L prime. So we have an S-free resolution of L prime. And we also have B1 to B0. That's a nice free complex. It's not a very interesting complex, but I'll call it B, script B. And now I claim that there's a map from any lifting. So let's call this matrix A. Take any lifting A to S. There exists a map. Let's call it B tilde. Lift of B to S. I can always do that because A is just a matrix of ring elements, so I'd lift them any old way, to L prime, but it's of degree -1. So what it looks like is L prime 0. This is a resolution of M prime, right, by hypothesis. L prime 1, etc. And now I can take B 0 tilde, that's the lift to S, B1 tilde, and a map. And I claim that there's a map here that makes this into a nice complex. Well, there's nothing to be said, right? There are no compositions in this complex. So what I've said is kind of empty. So I have this map. Let's call this map, I don't know, gamma. At the moment I have gamma from B of -1, properly speaking, to L prime. But I also have a map from the Cazul complex tensored with L prime, the Cazul complex of the F's, tensored with L prime to L prime, where K is the Cazul complex of F1 up to FC -1. Why is that? The Cazul complex is a resolution, because I assumed that the F's were a regular sequence, of R prime, and L prime is a resolution of M prime by hypothesis. So when I tensor them together, I get at least a complex covering R prime tensor M prime, which is just M prime, because M prime is an R prime module. So this is a complex covering M prime. And now I can take K, tensor B of -1 to L prime. Is this really what I wanted to do? Let's see. Yeah, that's right. To L prime. And the mapping cone of that is what I called L, upper arrow of M, F1 up to FC. Okay, that's the definition. This looks pretty awful when you write it in this form, but at least it's clear that I've constructed something, right? However, let me write it out in the case of codimension 2, and you'll see it's not so frightening. So here's the codimension 2 case. So in the codimension 2 case, well, I have to start the induction in codimension 1. I didn't say that. But in codimension 1, M prime disappears. There are no maximal Cohen-Macaulay modules over a regular ring without free sum n. So there's no M prime. There's just B1, B0. And so if you trace through this construction, you're just getting the old situation, B1 to B0. That's what I'll call B of 1. And that's a resolution of M prime in this case. M prime is now remember we're in codimension 2, we have F1 and F2. And M prime is a maximal Cohen-Macaulay module over S mod F1, so it has a matrix factorization, and this is it. This is the matrix factorization of M prime. And now what does the whole thing look like? Well, I have also a B1 of 2 mapping to B0 of 2. That was my new B. This you could call B1 of 1, B0 of 1, the codimension 1 situation, and a map. Here, that was the map, the comparison map that I put in. L prime is now the thing on top. And I have to put in the Cazul complex too, but in this case, it's the Cazul complex on one element. So that looks like just multiplication by F1, B0 of 2. Here's F1, and B1 of 2, and here's F1. And the Cazul complex is, the Cazul complex tensored with B is this. So if this is the map phi in the approximation sequence, then this is also phi. There's some minus sign somewhere because it's a Cazul complex. And the total complex is just the sum of these three pieces. Notice there are two layers. That's why it's called the layered resolution. Here's the top layer is itself an L upper arrow, and then it's joined by a lower layer, which is a Cazul complex times an L upper arrow. And that's the general picture. If I have time at the end, I will write it down, and I see I need yet another slide or two. Okay, so that was the upper complex construction. What about the lower complex construction? So L lower of M, F1 up to FC. Again, inductive. So I'll assume the existence of L lower of M, F1 up to FC minus 1. And again, I'll call it L prime. Sorry about that. L prime is now a free resolution over R prime, which is again S modulo F1 up to FC minus 1. Excuse me. And so I can make use of it. And now I use it again in the same style. So again, let's take M maximal Cohen-Macaulay over R, no free sum end, and M prime, the approximation, but with the approximation sequence again. So M prime plus B0, B1, the approximation sequence. And now I have the resolution L prime. That's a resolution of M prime. L prime 0, L prime 1, and so on. And once again, I can write B1 and a map to L prime 0. And now I don't have to take any tildes because this is all taking place over R prime. And if you think about it, the co-kernel of this sequence is clearly M, because B0 was, the map from B1 to B0 was exactly what I needed to complete the presentation of M from a presentation of M prime, and that's what this says. So now I have this is an R prime free resolution of M, not M prime anymore. And I know what to do in the codimension 1 case. I tensor with the divided power algebra on one generator. So I make a homotopy, choose a homotopy. That's an unfortunate part of this because it's an infinite choice homotopy. But maybe I can do something inductively to simplify my choice. Choose a homotopy for FC on this resolution, and then do the old construction from 1980, or also Shamish did this. So now Shamish, and my construction says you take this new complex, let's call this L double prime. L double prime tensor with the divided power algebra, which again I'll write as R of T dual, has the structure of a resolution. Of M, and now it's an R free resolution. And this is, by definition, L lower arrow of M F1 up to FC. And again, there are layers. The individual layers look like these box constructions tensored with L prime, tensored with divided power algebras. And one can make a whole structure out of that, but I think I'm out of time, and this might be a good place to stop. And thank you for your attention.
Thank you very much for a beautiful talk. Any questions?
One from me, from Srinivas.
Hi.
It does seem to depend on the choice of the generators. Is that correct?
Yes, very much so.
Can you?
Of course, when it's a minimal resolution, you get something isomorphic, independent of the generators. But you can define a sort of functoriality too. That's done in the lecture notes, Springer lecture notes.
I see. Okay, thanks.
So there is a category, rather messier than in the case of matrix factorizations in the old style, a category of higher matrix factorizations. But so far, no physicist has said this is what we need. So it may remain a niche interest. The whole matrix factorization thing was, slept peacefully along, constructing Cohen-Macaulay modules for commutative algebraists for many years. And then in, I think, the early 2000s, Kapustin discovered it. And suddenly there were 100 papers about it. The physicists are really voracious in this way. But the whole theory went in the direction of derived categories and such things. And there is a notion, a derived category notion of higher matrix factorizations too, where you work over a projective base. And essentially what you do is to replace F1 up to FC by summation xi fi, where the xi's are new variables. And that makes everything minimal, kind of automatically. But of course, it gives you no more information than you had before from the old resolution. So that, from my point of view, is not a very interesting answer, but it is an answer. Once you're in the derived category, you can't tell minimal complexes from non-minimal complexes. So this doesn't bother people in the derived category.
I have a question. So when you wrote this construction for codimension 2,
Yeah.
It reminds me of a homotopy category, two complexes. Is there anything to that, or it's just a illusion?
Let's see, where was that? Somewhere back here. It's after this. Hang on, let me get back to codimension 2. There. No?
No, it's still
Codimension 2, there it
yes.
is, written quite
Yes.
small.
Yes.
So, it's an interesting thought. I don't know about that. I mean, anytime you have a filtered resolution, which is what this is, of course, you could make spectral sequences. You could make, you can think about maps, these things as homotopy maps, but I don't know whether there's some natural.
I see this as a kind of a homotopy category. I mean, I see that in front of me. Of two chain complexes.
Yeah.
So if you write for codimension 3, you'll have 3 layers.
Mm-hmm. That's right. That's easy to write down and looks more or less the same. So you'd have so in codimension 3, you'd have a B0 to B1. Oh, I didn't put in all the maps before. Let me be more honest this time. You'd have a B1 to B2. Sorry, B0 of, I'm doing this completely wrong. Let's try again. B1 of 1 to B0 of 1. That's layer 1, right?
Mm-hmm.
B1 of 2 to B0 of 2. And there's a map, and then there's a Cazul complex attached to that, B0 of 2, and F1, and B1 of 2, and F1. And there's another map here, I should have said. So there's a whole map between these two layers. Now the third layer will look sort of similar, B0 of 3, and B1 of 3, and then there'll be a B0 of 3 plus another B0 of 3, and F1 and F2. And this goes on as a Cazul complex. So there'll be another, this is, before we had, this was the 0, then this is the Cazul complex on one generator tensored with B1 to B2. Here we have the Cazul complex on 2 generators tensored with that. So we have another copy of B0 of 3 out here with F2 and F1, and yet another copy of this whole Cazul complex coming from B1 of 3. So there'll be 2 copies of B1 of 3. Sorry to make this so small. Obviously didn't plan my space very well. And yet another B1 of 3 out here. Okay, so now the complex has length 1 more, as it must, because the codimension 2, so we must be writing down the resolution of something of length 2. So there's going to be a 0, 1, 2, sorry, length 3, 0, 1, 2, 3. And this is the only term in the third free module in the resolution. So this all will map up to what came before in a complicated way. And finally, there'll be a map from here to here. So that's the picture. And you can do a similar thing with the layers of the lower resolution. So this was the upper resolution. By the way, there is a Macaulay 2 package which does all this, called Complete Intersection Resolutions, if you want to see them explicitly.
So you don't see a triangulated category here coming. There's a shifts here, and I see triangles. You don't see any such thing.
Well, anytime you make a derived category, you get triangulated stuff, and the homotopy category of complexes is that category.
Yes.
But I don't. I mean, so there is a nice category of matrix factorizations. So in that sense, yes, but this individual complex doesn't. I don't see that. I don't see how this is a category exactly, or why one would want to look at it that way.
I see. Any more questions?
There is a question in the chat box.
Oh,
Sorry.
Yeah.
let's see. I'm not looking at the
I
chat.
don't see it.
I know. Why is the canonical module mysterious?
That was already addressed.
David answered it in the talk.
I
That was
tried
addressed
to
in the-
answer it. I waved my hands. One of the first pieces of research I read by Jürgen Herzog was his wonderful little Springer notes with Kuntz on canonical modules of one-dimensional Cohen-Macaulay rings. And that already gave me respect, let's say, for the canonical module. So there are many situations in which you can describe the canonical module explicitly. But in general, I claim it's less obvious than a free module, for example.
And also, in your construction, to get the minimality, you don't require complete intersection. It's only for the periodicity, as I understand.
No,
And
you
you
require
got
complete intersection. And a high syzygy of a module. So you always have. The natural question is which syzygy works, right? In the complete intersection, in the hypersurface case, we had to go back far enough to make a maximal Cohen-Macaulay module without free summons, and then we got periodicity. In the codimension 2 case already, there is no uniform bound, but you can bound it in terms of the regularity, Castelnuovo-Mumford regularity of an X module over some polynomial ring. So that's a whole nother story, but there's a regularity that creeps in, and you can see that that's necessary because in codimension 2, you could take for example, the resolution of the residue field. Let me add one. Yeah, there we are. So you can take the resolution of the residue field in codimension 2, R2, R3, R4, etc. And since it's a Gorenstein ring, a complete intersection, you can do it backwards too. So you can go R, R2, R3, and so on. And the way this construction works, it can't possibly be minimal if you apply it to this module. You have to be back here to make it minimal. I guess it's periodic after this, or grows. So if you start from here, you get minimality. Minimal from here. In other words, if you do this construction for this syzygy, you get minimality, but for no syzygy further to the right, and there are infinitely many of them. So you might have to take an arbitrary number of syzygies before getting to one where minimality will hold, and that's just a fact of life. But it's interesting to speculate what might be this point in the resolution. So there's obviously a best place in this resolution, a most zero place. And Avramov and company have worked on such things. I don't think they have the full answer yet, because you can take direct sums of this with shifts. You can make life more complicated. But but there's always a kind of middle of the resolution and then the ends. The ends look like the asymptotic part and the middle looks different. And really describing that is for me a very interesting question. I thought for a while that I could just take the S2ification of the X module and see how that worked, but that doesn't quite work. So this remains an interesting question. What is the middle and what are the ends of this infinite free resolution? Do you have a good answer to that, Graham? I see you smiling at this question.
No, certainly not. No, I mean, in some sense, this is what the singularity category is for, right? That it throws away the ends and tells you what the relevant part of the middle is. But now you're living in a derived category and for some weird triangulated place. So yeah. it may have the answer, but you can't read it.
Well, I thought of the singularity category as throwing away the middle and keeping just the ends, right? Because you replace a module by a Cohen-Macaulay module, which is a far-out syzygy.
You're right. I misspoke. It's the other way around. But yeah.
So it's the part you threw away that somehow contains all the extra structure of the module category. Maybe too complicated for us ever to understand, but tempting. Yeah.
Any other question? Okay, we thank the speaker here for giving a beautiful board talk. I never thought that this is possible with a board talk. It's fantastic.
Very good. Thanks for listening. Nice to be there again. I remember my visits also to IIT Bombay very well. Lovely place.
Thanks, David.
I hope to be back sometime after this crazy pandemic is gone.
Yeah.
Okay. Take care. Be
See
safe.
you, everybody. Bye-bye.
Bye-bye.
Bye-bye.